Okay, hi everyone. My name's Octavia. I'm a principal security engineer here at Prelude Security. We're joined today by Moloch, who will be talking about offensive Wasm in the Sliver C2 framework. Joe, thank you so much for coming out to meet with us today. Really excited to have you here. So with that, I'll hand it over to you. Floor is yours.
Yeah, thank you for having me. Appreciate the invite. Yeah, so my name's Moloch, and then some people also call me Joe. I'm a managing principal at Bishop Fox, where I oversee the red team practice. Where I oversee is sort of like the technical aspects of the red team practice here at Bishop Fox. I've been at Bishop Fox for about 12 years. Started as an intern, and yeah, stuck around, and actually helped start the red team practice about 3 years ago now here at Bishop Fox. Prior to that, my background's actually in application security, so it's a little different than I think a lot of the folks in the red team space. I really, started my career doing security consulting work for tech startups in the Bay Area as well as large tech companies. And so I ended up like getting introduced to a lot of sort of like hipster technologies, no schemaless databases, and I think that's kind of where, or I kind of that's kind of why I think I like Go and some of these like fancier, more modern stuff is just because like my background's in kind of like this fancier stuff, but or like the newer stuff. We also do like a lot of serverless stuff at Bishop Fox, and we do a lot of cloud security as well. So that's kind of my background. I also did quite a bit of work in on iOS security. I've been out of that game for a few years now, but I wrote I co-authored iSpy, I should say, which is like a code injection and reverse engineering framework for iOS applications. Just use Frida now, though. It was like this is before Frida came out. It was like a janky version of Frida. But yeah, Frida's like witchcraft now, so definitely use that. But that's kind of my background. General like web application technologies, iOS security. I've done a lot of work in cryptography. Slightly less in like cryptocurrencies, but I've done a lot in actual cryptography. So, and yeah, I've been doing red teaming for about the last 3 years. And in my spare time, I'm a big open source advocate, and I'm the lead author or lead developer for Sliver, which is an open source command and control framework for written in Golang, as we kind of alluded to earlier. Yeah, we use it. Again, we always try to use the right tool for the right job. Programming languages are just tools, just like anything else. Every programming language has certain advantages and disadvantages, and so we always try to weigh those. Yeah, so I chose Go for Sliver for a variety of reasons, which I actually have a separate presentation about that. But let's kind of put all of that stuff aside for a little while and just talk about WebAssembly. So forget about red teaming, forget about command and control frameworks, all that sort of stuff. Let's talk just sort of about what is WebAssembly. And again, my background's in like web application security, so this is kind of like I've actually been toying around a lot with WebAssembly since it came out a few years ago, but there's been a few missing ingredients, and now I think it's really starting to get very interesting in its applications when it comes to implementing offensive security tooling, and the things that you can do with it are really cool. And I think just generally speaking, it's a really interesting technology from a security standpoint. So again, red teaming aside, I think there's really interesting things about WebAssembly for security in general. Not just for creating malware and things like that, but just generally speaking. So, what is WebAssembly? What's kind of going on here? So, if you're unfamiliar with WebAssembly, it's basically a way of taking existing code bases and running them in the browser. And these are typically languages that you would otherwise be unable to run in the browser, right? Because JavaScript's pretty much your only choice in the browser. Like, yes, you can transpile things into JavaScript and all this sort of stuff, but and actually, WebAssembly started out as ASM.js, and ASM.js was a subset of JavaScript for Firefox that allowed certain optimizations to the runtime. So if you're familiar with JavaScript, it's a pretty terrible programming language. It has almost no redeeming qualities. It doesn't even have an integer type, right? All it has is a float, a number. It's a number type. It's not even an integer. It's a float. It has weird overflow behavior and all this sort of stuff. So this was like some of the challenges when it came, because JavaScript started to get pretty fast in the early sort of 2010s. And this is because, Google and other companies poured millions of dollars into putting more lipstick on the pig that is JavaScript. So but the execution actually became pretty fast. And so people wanted to use it to do more interesting things. And, running games in the browser, and around this time, like Flash was getting deprecated and stuff. And so Mozilla actually came up with Wasm.js, and it was like this subset of JavaScript where you could have like these hints to tell the compiler or the runtime rather, or the just-in-time compiler, like, hey, this is an integer. I know you think it's a number, but it's an integer. And this allowed them to compile a C code into this subset, this Wasm.js. And one of the first demos they did is they compiled Unreal Tournament to Wasm.js and ran it in the browser, which was super cool. And so this was sort of like the very, very early sort of prototype for what eventually became Wasm, the standardized Wasm. So Wasm also often gets compared to things like Flash and Java applets and things like that, although there are quite a few differences. So, Wasm isn't really connected to any language. It's meant to be compiled to. It's meant to be a compiler target. It doesn't really have any language associated with it in the same way that Java applets are associated with Java and Flash is associated with ActionScript. That's not really a thing. So it's slightly different in that way. It's a lot closer to like LLVM intermediate representation than something like a Java applet. So we can take a lot of existing code bases and compile them to Wasm. There's a lot of really cool examples of this. If you go to playcs.com, there's actually an entire implementation of Counter-Strike 1.6 running in the browser, which is super cool. I think they implemented an x86 emulator to do this. I'm not exactly sure because I think it's running like the actual game files. But if you go to playcs.com, you can play an entire version of Counter-Strike 1.6 running in the browser at 60 frames a second. So this is one of the other sort of like interesting properties of Wasm, which is that its execution speed is good. Like it's not quite to native speed, although we'll talk about performance more later, but execution-wise, it's pretty performant. It's designed to be loaded over the network, right? Because all this stuff's running in the browser, right? So certain properties that are required for Wasm are, it needs to be loaded directly into memory because the browser does not have access to a file system, right? You're loading everything over the network, so it has to get loaded directly into memory. So that means, it needs to be relatively small and compact and easy to parse and easy to load over the network. And then it needs to be fairly performant when it actually executes. And you can probably start to see why some of these properties are interested to offensive tooling developers, because we often want to load things over the network. And performance is usually not that important, but can be a nice attribute as well. So, and there's been some other really cool, exciting work done in this area. So for example, OctoPwnWeb is super cool. He has they actually compiled like an entire RDP client, which you can see on the left here. Like it's a full RDP client running in the browser, which is super cool. They have a nice interface here, and they've compiled a lot of Python tools, or rather, there's a version of CPython that's been compiled to Wasm, and then since Python code is a high-level language that runs on an interpreter, as long as you have a Python interpreter, you can run the code. For the most part, we'll again talk about this later. So they've taken a lot of the Python tooling, and you can actually just run it in the browser now because there is a Python implementation. You can take a C client or an RDP client that's written in C and compile that. But kind of the architecture here is, this is all kind of on the operator side. And then there's some magic that happens for the socket connections. They get tunneled over a WebSocket. They go through a program called WSNet, and then that kind of tunnels the connections out to the target, right? So super cool, but all of this is kind of happening on the operator side or on the attacker side. You can basically do an entire pen test, from your browser, which is kind of crazy. But we're sort of limited in that we need to tunnel all the connections into the target, and we still need some native code to do that. So really exciting stuff. Interesting, like super interested to see where this goes. Because again, Wasm is also, since it's running in the browser and everything, it's also CPU architecture independent and operating system independent, which is super interesting as well. So, but just some quick terms, some definitions. So Wasm is specifically the binary specification. There's also WAT, which is the textual representation, also of the spec, and then WAST, which is a superset. It's not part of the formal specifications, but you do see it around, and a lot of the tools will output WAST. Think like high-level assembly. It's very similar to WAT, but has some syntactical sugar. It's not quite a one-to-one representation. And then WABIT is the binary toolkit for Wasm, which is available on GitHub here. And this includes things like assemblers, disassemblers, all the types of like plumbing. It's kind of like a Swiss Army knife for Wasm. So some important characteristics, though, or attributes of Wasm, right? You have to use, again, just speaking about Wasm in the browser specifically, right? So we're just talking about Wasm in the browser. You do still need JavaScript to load it. So it's not quite a full replacement for JavaScript, unfortunately. We still have to stomach a bit of JavaScript. It also has access to nothing by default. It can't even manipulate the DOM by default. You can expose things to the Wasm runtime. And similarly, the Wasm runtime can expose functions back to the JavaScript runtime, but everything is denied by default. So by default, Wasm just kind of runs in a vacuum. It has access to nothing, and it can't really do anything outside of its own runtime. The JavaScript runtime has to expose functionality to it or do something. It's all basically, just runs in a vacuum if you don't do something. So, which is a very good design principle from a security standpoint, right? And I think this is also why Wasm's not very interesting from like a cross-site scripting sort of standpoint, or from like a web application security standpoint. They did a pretty good job of designing this, and you really have to go out of your way to make some of the stuff in the browser again vulnerable. So, but if you look on the left here, that's what WAT looks like. It has an infix S notation to it, and then on the right there you can see the Wasm, which is the binary. And then in the lower left, you can also see the JavaScript, which loads the Wasm module. Again, here it's calling a function which is exported by the Wasm called add2. And then, the JavaScript is calling it, right? And Wasm typically will execute faster than JavaScript. So, this is a pretty basic example, but it's not necessarily that unrealistic. You might want to do stuff like this. So some of the other interesting, components here. Hold on, where's my slides? Oh yeah, there's the JavaScript. You can see how it exports things. And this is why, again, it's denied by default. So it's designed pretty well. The other interesting security standpoint here is that this is sort of the computer architecture. So not the CPU architecture, but there's also, a concept called the computer architecture. And WebAssembly is implemented using a non-von Neumann architecture. So von Neumann architecture is a very fancy term to describe a computer which has, it uses the same memory for data and instructions, right? So in our case, it would be like RAM, right? And if you're familiar with like injection vulnerabilities, right? So all injection vulnerabilities occur because the computer cannot accurately differentiate between what's an instruction and what's data, right? So like SQL injection, the SQL interpreter can't accurately differentiate between data, usually user input, and SQL instructions. And the way that you fix this, right, is you use a prepared statement which clearly delineates what's the instruction versus the data, because you have to like bind types and things to it, right? It's the same with native memory, right? A buffer overflow is a type of injection vulnerability. It occurs because there's instructions in data, on the stack, and you can overwrite instructions and things like that. And a lot of modern memory protections are actually trying to graft protections onto the computer to make a differentiation between these two things, right? So like the NX bit, right? The non-execute bit is trying to mark regions of memory that are only supposed to be data. But these are all kind of half measures because all modern systems, ARM, x86, are the von Neumann architecture where you have basically unified memory for instructions and data. However, there are other architectures, notably like the Harvard architecture, like you see here, which actually just has separate memory for instructions and data. And so things like buffer overflows are not exploitable on this architecture. And this is the architecture that WebAssembly actually uses. So you can take existing C code and compile it to Wasm, and certain types of vulnerabilities just go away. Namely, things like buffer overflows, at least when it comes to executing arbitrary code, are no longer a problem. Out-of-bound writes are still potentially problematic, right? Integer overflows are still potentially problematic. You can still have race conditions, right? So it's not like you get to stop worrying about security. But as far as like leveraging a buffer overflow to get arbitrary code execution, it's just it's not a concept anymore. Because there's no way to address like an instruction. Like it doesn't live in any addressable memory that your instructions can actually access. Similarly, the stack is, different memory. Obviously, this is all running on a von Neumann architecture still, right? Because this is a virtual machine. So, barring implementation bugs, which there certainly have been some in the past, but a lot of these are, implemented in Go or in Rust. It's a very difficult target. It's a very interesting target from a security standpoint, especially because it can run existing code. It can run legacy code. You can take existing C applications and compile them into Wasm and kind of constrain them in really interesting ways. And this is where we start to get outside of the browser with Wasm, because it has this really interesting sort of design to it. And if you think about how to sort of implement isolation on top of existing programs and things like that, you typically think of virtualization, right? And there's different sort of levels of virtualization. You have hypervisors, which are sort of the deep magic of the internet, right? They're these very low level things that abstract hardware at a very, very low level, and you have kernels running on top of them, right? It's like really, really intense stuff. Typically, the end user will, the heavyweight version of this would be a virtual machine, right? This is typically where normal users start to come in. More recently, we've had containers. Containerization is very popular. These also allow some level of isolation for a process, right? It's still the same kernel. You're still talking to a kernel, but you can, you can disable certain system calls and things like that. But containers are still relatively they're sort of the middleweight abstraction here. You still have a file system. You still have a kernel that you can talk to. You have to configure a lot of things. So perhaps there's another, category here for very lightweight virtualization and isolation. And that's kind of where people started looking at this Wasm design. It has this interesting memory design, and you can compile C code to it. So maybe there's some opportunity here. And this is where WASI steps in, or the WebAssembly system interface, which is really a way of, it's really analogous to a system call in an operating system. So, normally you would have a user space process. It wants to perform a file open or something, right? It makes a system call to the kernel, and the kernel facilitates that. So WASI is sort of that for WebAssembly. And it's meant to be extensible as well. So it's not necessarily just file systems, although we'll talk about the file system the most. But really, it's basically a system call interface for anything that you would want. However, interestingly, from a performance standpoint, this is all occurring in the same process. So there's no context switch which occurs. So normally, when you make a system call, there's a context switch to the kernel. That doesn't occur in WebAssembly because it's all in the same process, right? So kind of interesting there because context switches can have a material impact on performance. So this is kind of what it looks like in the browser, right? We have the V8 runtime if it's Chrome. It loads a Wasm module, that Wasm, and it can expose functions to the Wasm module, and the Wasm module can expose or export functions back to the V8 runtime, and then it can call and ask it to do things, right? And that's kind of how that works. So what WASI allows us to do is it kind of turns into this setup where we have some arbitrary program runtime, and that program's runtime can export functionality or expose functions to the Wasm module, and the Wasm module can make calls back to the program's runtime through WASI, right? Because we have to compile this code ahead of time, right? So if we have C and we want to open a file, the C compiler needs to know what the call signature is for that file open in order to perform the system call. And so WASI basically standardizes all of this, right? You could do it bespoke too, right? So you could have a bespoke file open that accepts, any argument, but all of your code, all of the existing code has to be updated or monkey patched in some way in order to know the call signature for that file open. So WASI just standardizes that and allows the compiler to know the call signature for something like file open ahead of time. And it contains all sort of the piping around, file manipulation for that. So it kind of turns into this picture, right? So on the left, you would take a C program, you would compile it with CLang. The compiler knows, assuming it supports a given operating system and architecture, it knows how to perform those system calls or call the appropriate libraries or whatever. And on the right here is kind of the Wasm approach, which is you compile the C code to Wasm, and then the Wasm runtime abstracts the operating system. So this is a kind of the other interesting thing, is that it abstracts the operating system entirely. So what you'll typically find with WASI is it's the least common denominator amongst all the major operating systems. So more advanced concepts like file system permissions and stuff may not actually be in the WASI specification, tends to be the least common denominator, but it's enough to get a lot of work done at the same time. And we can take the same file and it runs on every operating system and every architecture. So this is where WASI is at least designed to sort of come in, and Wasm, and actually Docker already supports Wasm. There's like a beta release of Docker that already supports executing Wasm modules instead of full containers. So you're already starting to see companies ship products around this, and I think it will become more popular in the future. So it's just a really interesting technology. It definitely has sort of a secure by default mentality. It also emphasizes safety over only security, right? So safe technology is a secure technology that's difficult to misuse. Something like TOTP or code-based two-factor authentication can be phished. So it's secure, but it's not necessarily safe. Whereas like a YubiKey or U2F, that's safe because you can't phish it, right? So lots of really interesting applications here. So, all right, let's bring it back to offensive tooling. How can we kind of start to incorporate this into offensive tooling? So the first sort of use case that I came up with is traffic encoders. And we'll talk a bit about how these work. But I've always felt that, malleable C2 profiles have always been a bit limiting. They don't provide enough control, in my opinion, over the generated traffic. So sort of my first attempt at this was using procedural generation, which is what Sliver uses, right? So every request is randomly generated, or from some seed data. And this has some marginal benefits in that not every request looks the same. Even if you capture traffic from one implant, it's not going to look that close to the traffic coming out of another one, even though they're all potentially using the same configs. So traffic encoders, though, what I wanted to do is basically provide a way for the end user, the operator, to define callback functions that can arbitrarily modify the implant's network traffic. And basically what this allows us to do is use Turing-complete full programming languages that we can embed at compile time in the implant to perform any arbitrary modification to the network traffic. And these can be implemented in Rust, in Go, in TinyGo, in Zig, basically any language that compiles to Wasm. And you just have to implement this interface, a decode function, an encode function, and then a malloc and a free, depending on the language, because some of the malloc and free may be handled for you, depending on the language. And kind of the cool thing here is that these functions, these WASM modules, are loaded by both the server and the implant, right? Because WASM is, safe, and we can load it on any operating system and any architecture. You just define these functions, and actually the server, like you load the same code on both sides of the network connection. And as long as the encode and decode functions are inverses of each other, we can arbitrarily encode traffic in any way that we want. So the way that this is implemented is there's an encoder ID, which is basically the lower 32 bits of the SHA-256 of the WASM module, right? Because we have to make sure that we're using the same WASM module on both sides and the same version of that WASM module. So you can also load an arbitrary number of these functions or modules on both sides of the connection, and they can be loaded at runtime. So we can actually push new traffic encoders to the implant at runtime, after it's deployed in the field, and arbitrarily modify the traffic for the future. So it doesn't even not necessarily have to be compiled in. So basically when the implant wants to send data to the server, it calculates the encoder ID. It then calls encode or the encode function in the module. It sends that traffic to the server. The server loads the same module based on the encoder ID. It calls the decode function. And then when it wants to send traffic, or if it needs to send traffic back to the implant, it just uses the same module and calls encode on the data and passes it back. And in this way, we can ensure that the same traffic encoder is used on both sides of the connection. And we can redefine traffic. We can redefine it at runtime any way that we want. So here's a very basic example. It's not very exciting, but so we have our encode and decode function. This is implemented in Rust, obviously. I actually do recommend Rust for this because it tends to be, I've gotten the best performance out of Rust. And I do have examples of this in the Sliver repo. So you can play around with it if you want. But basically, we're just hex encoding a buffer, right? So the encode function, accepts an input, which is just a slice of bytes, and it returns a slice of bytes. And the decode works the same way, right? Because we're just manipulating bytes in, bytes out. That's all we care about. And in this case, we can perform any operation that we want. We're just hex encoding it for, demonstration purposes. I don't know if this video is going to come through, but we'll try it. And I will pause at key points so hopefully the frame comes through. So here you can see we run generate traffic encoders. There's no traffic encoders loaded into the server. So we're just going to add our traffic encoder called hex.wasm. And so when you load a traffic encoder onto the server for the first time, it runs basically some unit tests to ensure that the encoder function is actually working the way that we expect it to. So it'll randomly generate some data, pass it through the encoder function, then call the decode function and make sure it gets the same data back and that there's no data corruption occurring. And then we also test the performance. If you're not careful, there can be some pretty significant performance impacts here. And while that may not be a problem in beacon mode where we can, eat the network latency, generally speaking, Sliver also kind of supports real-time interaction. And if we have to wait 5 or 6 seconds to encode, 100 bytes of data, that's obviously going to not really work out so well. So whenever you load a new function, and these can be specified by any operator on the server, we just test that, make sure everything's working. And then from there, when you go to generate the implant, as you can see here, we're just going to specify whichever traffic encoders we want to include, at least by default. And I'm also going to enable debug mode here. We're using HTTP. We're targeting Mac OS on ARM64. There we go. We generated it. So we'll start our listener, and then I'll just run the implant. You can see some of the debug output here. We get our session, and we can start interacting with it. So we'll, list the current working directory. And if we look at the burp traffic, which is capturing all of this, you can see that this is it's all hexadecimal encoded, right? Because it's using the traffic encoder that the operator specified. And in this case, again, hopefully the video is coming through. It's actually fast enough to keep up with real-time connections. You can also see here, we're still using some procedural generation in the URLs. Every URL is different, never sends the same value twice. But we can also do real-time interaction with shell and run top through our custom encoder. So if we go back to the network traffic here, you can see it's still using the custom encoder for all of the network traffic. And you can see top updating in the background there. So this basically, allows end users to sort of arbitrarily define what network traffic looks like in the next version of Sliver, which I think is pretty cool. So obviously where we can take this from here is implementing a full HTTP client. Right now, it just it only controls the body of the request. But obviously we can expand this, and then implementing full sockets in TCP would be very cool. This is also how we're planning to implement a third-party C2, because after you have an HTTP client, you can implement, you can tunnel the traffic through Slack or really anything that you want at that point. So it allows, arbitrary third-party channels to be implemented as well. But there's actually more. So this was kind of my first cut at using Wasm in sort of like an offensive security setting. But, I think there's other equally interesting use cases. So in addition to that, I've also implemented extensions using Wasm and WASI, right? Because the traffic encoders just use Wasm, right? It's a custom interface. It's a custom call signature that I specified. You have to implement my interface if you want it to work, right? So WASI is the spec. And where this kind of comes into play, right, is there's some drawbacks, right? So there's different types of extensions that we would typically want to load at runtime. Beacon object files or BOFs are obviously some of the more popular ones. There's some disadvantages to these, though, which is, if they crash everything, right? Because you're loading that code into your process. So there can be stability concerns from that standpoint. It's also, BOFs basically only work on Windows. I mean, you could load a COF file on any operating system, but it's basically all of the implementations, including Sliver, only work on Windows. So it's platform specific, and it is very stealthy. That from that standpoint is pretty good. We also have native extensions. So this is something Sliver supports today, which is, again, you have to implement the Sliver interface, but it can, reflectively load a DLL at runtime, and then call functions and get data back, and then pass that back through the existing C2 channels. Again, we're loading code into the existing process. It's native code. If it crashes, again, we're back to stability problems. It's slightly less stealthy than something like a BOF, but it's still at least getting loaded directly into memory and everything, right? So this is where I think Wasm extensions start to become a bit more interesting, or at least, they're a good third option. There's still use cases where you probably want to use these other options. But Wasm seems like it's becoming, and actually in the future, it'll even get even better, but it's starting to become a really interesting option for implementing extended functionality in sort of a generic sense, right? So beyond traffic encoders. So this is kind of what it looks like, right? So the other interesting thing is that C# also now compiles into Wasm. And so we can actually execute C# tools without loading the CLR. If you're familiar with EDR and telemetry and stuff, a lot of the detections for C# tooling relies on detecting the CLR. And so Wasm, if you compile it to Wasm, there is no CLR. It's gone. And it also loads in process by default, which is kind of cool too. So, so kind of the missing magic ingredient here for implementing this was zero. And zero is a zero dependency Golang implementation of Wasm. So it's written in pure Go. It implements the Wasm specification, and it has no dependencies. So we can easily embed this into the Sliver implant and give it a Wasm runtime. So with zero, And we can maintain all sort of the cross-platform nature of Go and Sliver, right? So if you're unfamiliar with Sliver, it can generate implants for Mac OS, Windows, Linux, Solaris, Plan 9, iOS, Android, basically anything that Go compiles to. And since WAS0 is implemented in pure Go, we can generally compile it to any of those platforms. There are a few limitations there, but so it's really interesting from that standpoint. So we can compile a single extension and it runs on everything. So also, so the first thing I did was their CPython supports, Wasm. And actually, Scythe has a really great blog post or article from a couple of years ago on doing basically loading a CPython interpreter in memory for offensive security purposes. And how do you patch imports, right? Because even if you load an interpreter, you still need to import libraries and stuff. And like, how do you patch that and do all that? But there's significant limitations in this, in that it takes quite a bit of modification. You have to monkey patch things. And even if you go through all of this work, it only runs on Windows, right? It's all Windows sort of specific changes that need to be made. However, what we can do instead is we can take the Wasm CPython interpreter and just run it in WAS0 in memory. And now we have a CPython interpreter that runs on every operating system, every CPU architecture, and gets loaded directly into memory. And so the other thing that I did, right, is obviously we're still going to want to import stuff, after we load it on target, we still want to import stuff, but we also want to access the remote file system, right? Because this is like post-exploitation tooling. We probably want to have access to the file system and manipulate files on disk and stuff like that. So what I did is I implemented a virtual file system using the WASI specification. So inside the Sliver implant, when we load one of these Wasm extension modules, and that module attempts to access the file system through the WASI system call, which the system call, again, just goes through our process. We intercept that and we look at the path that the code is trying to access. And if the path starts with memfs, it gets redirected to an in-memory virtual file system that I implemented in the implant. And if it doesn't, it just gets passed through to the host operating system, to that file system. So the code still thinks it's running on the remote system, on the remote file system, but you can access sort of like the secret region of the file system, which can only be seen from inside the Wasm module, right? Because this is all in memory. Nothing else can see this file system. No security tools or anything can see it. So we kind of get the best of both worlds. We can, pack libraries and stuff into memfs, import them at runtime, and then manipulate files on the local file system. And so here's sort of a video of how that works. So again, hopefully these are coming through. But here I've generated two implants, one for Windows and one for Mac OS. We already have sessions up as well. So we're running we have two sessions, two implants, one running on Mac OS ARM64 and the other running on Windows x86. And so what we're going to do is we'll just interact with one of these sessions. So we're going to start with Mac OS ARM64. And you can see here, I'm just specifying Wasm. I'm going to include the test.py file, although we'll come back to that later. So on the left there, this is how you include files into that virtual file system. Then we're specifying the extension that we want to run. In this case, it's literally just CPython. Like I didn't change any of the Python code. All I did was compile it to Wasm. And then on the right there, you can see we're using -C because it accepts command line flags, just like everything else. And then we'll specify some inline Python code that we want to run. In this case, we're just going to list the memfs directory. And what we should see is that test.py is there on the remote system. So I'm just going to run this quick. So it's sending the module, and there you can see it executed, and it sees the test Python in that directory, right? So, and again, this is just Python code. We're using Python's OS list dir, so it clearly thinks it's a file system, even though it doesn't exist. And any code that we run, still has access to the local file system as well. And then we can even tell it to interpret these files as though they were, normal Python files. So if we want to execute the test.py file, here it is. It's just a hello world, program. We just specify it like we would a normal, file. We just specify the file path, and you can ignore those errors. I'll fix those later, but you can see there it executed the Python script. And then we also stream standard out. So you can execute these interactively as well. So I added interactive support, so you can actually bind standard in, standard out of the operator's terminal to the Wasm module, and you can run interactive programs and interact over the C2 channel with the Wasm module, or you can just execute it, capture the output, and send it back to the server. So both modes of operation are fully supported. And you can see here it's executing we have a full Python interpreter in memory on macOS ARM64. And yeah, so I think that's pretty cool. But even cooler, right now we can switch to Windows and we can run the exact same commands and with the exact same files. We don't have to recompile anything. We don't even have to change the files. We'll run that Python script again, and it'll load and interpret the Python interpreter in memory. Again, all of this is in memory, in process, and we can execute arbitrary Python code and import arbitrary libraries from the virtual file system. So there again, you can see again, ignore the errors, I'll fix those. But you can see there again, we're executing the Python script from the virtual file system on the remote machine. So yeah, so this kind of gives us a write once in any language, run in memory, in process anywhere type of primitive. Because again, really we're running C code here because we're running C Python, right? We're not, obviously we're running the Python code, but the main thing that's actually in Wasm, right, is the C Python interpreter. That's why we don't have to change really any of the Python code. We just have to compile the C Python interpreter. So obviously there's definitely still some significant limitations here. The biggest one right now is there's no socket support. So the sockets is being standardized, but it's not quite standardized yet. So we can't make any network connections yet unless we can monkey patch and implement it ourselves if we want. But right now you can't take existing tools that perform network connections and get them to run in Wasm yet. But the socket specification is almost finalized. I think we'll have it in the next 6 months or so, hopefully. And then even that should start to work. And that's where I think it'll really start to pop off for offensive security tooling. Because while it is nice to like tunnel all of your connections, and do everything the light touch, you often run into situations where you just want to be able to run things on target. It's just going to simplify stuff if you run it on target. And this obviously makes it a lot easier to do that. And again, I think the .NET tooling is another good example where I think it'll have a second life once the CLR dies, because it's much more difficult to detect. Well, one, there are no detections for Wasm right now because it's kind of so new. But two, it's just an interpreter in a process. It's not loading any libraries, right? The other thing about this is we're not calling load library. We're not loading anything really as far as the operating system is concerned. We're not, this is all in process code baked into the implant. We're not calling any system libraries or anything like that. So it's very difficult to introspect and detect. And that's before we really even start to apply obfuscation techniques to all of this. Which you certainly can. So, all right, so where's this going? What's the future look like? So that's kind of where we're at today. What's the future look like aside from socket support? So this is kind of what, this is the Sliver architecture, if you're unfamiliar with it. It uses, all of the comms as far as the client to the server, gRPC over mutual TLS. And we do try to maintain a trust boundary here. So we don't make any assumptions that we try to prevent the operator from executing any code on the actual server. And this is so you can potentially have a white team, and maintain the integrity of the logs and things like that on the server. Obviously, they can access anything on the implants, but it's not a foregone conclusion in our sort of architecture that the operator should be able to run any code on the server. So we maintain a trust boundary here. And one of the sort of drawbacks of this is that if you want to write, so Sliver also has an event-based system. So there's a command built into the client called reactions, which allows you to specify commands that you want to run when some event is triggered. There's also a Python library called SliverPy that allows you to execute arbitrary logic whenever some event occurs. That could be, a new beacon or really anything. There's a lot of different events in the event system, but it allows you to react to things in real time. The disadvantage to this, right, is that if I run some automation, and also, all functionality within Sliver is programmatically accessible as well, because everything's implemented through this gRPC interface. So a SliverPy script can do anything that the operator can do. And you can execute that logic when some event occurs. So, but the disadvantage here, right, is like if the operator's laptop goes to sleep or something, that connection dies, and now you can't react to anything, right? Because if they're running it remotely, right? I mean, you could always run SliverPy in the server, right, and have it, run the automations there. But we have this trust boundary. It's not a foregone conclusion that the operator has access to the server. So one of the other interesting things we want to use Wasm for is actually server-side logic extensions. So the operator will be able to find, arbitrary logic that they want to invoke on some event, and the server can actually load that code and run it for the operator, and the operator can, go have coffee or something, right? Since we were using gRPC, there's actually already a Go project that can take a gRPC interface and generate a Wasm module for you, which is super cool. So we actually this is perfect, right? Because those gRPC interfaces are the ones that you need to call. So we haven't quite done this yet, but it's looking quite promising. And I think this will pair well with some of the other stuff that I'm adding to the new version of Sliver. So I've also added a custom hashcat sort of implementation so that you can connect GPUs to the Sliver server. That way, when you run, Kerberos or something, that triggers an event which queues that ticket on the GPU cracks it and, returns the password to the server, which triggers another event that, triggers some lateral movement or something like that. So I think the two will be an interesting combination, being able to define arbitrary server-side logic in addition to some of these extra capabilities that we're working on adding to the platform. So anyways, that's kind of the future. That's kind of where we're going. Real quick, I think another interesting, I don't know if you guys ever used Mirage OS I started programming on a calculator. That was my introduction to programming, as I wrote equation solvers and then sold them to my friends. But anyways, so no, not that Mirage OS, this Mirage OS, which is a unikernel sort of library. And basically so what Mirage OS is it's basically a virtualization system that can boot a full virtual machine for every TCP connection. So it only takes a couple milliseconds to boot a virtual machine. So what they do is every TCP connection that comes in, they just create an entire virtual machine to handle that connection, and then they destroy it as soon as the TCP connection closes. So I think this also becomes very interesting with Wasm, right? Because you can implement Wasm in this, and now you have Wasm running basically in kernel mode. Again, we can avoid any context switches. So it might actually run faster than native userland code, like on a server. And you get this sort of interesting isolation between the different virtual machines because it only takes a couple milliseconds to boot them up and execute stuff. And again, you can take existing code bases and run them on this platform without really much of any modification. So I think that'll be a really interesting target in the future, is these sort of ephemeral kernels that can execute purpose-built applications. So anyways, so all the code is available in v1.6/master on our GitHub if you want to play around with it. All of the demos and stuff I showed today are implemented in there for you to play around with. I don't vouch for the stability or anything of this code until we merge it, until we release, a full version 1.6, which will be ready whenever we finish it. Sliver is really more of a side project. And so we kind of just develop it whenever we have, free time and stuff. So, but I think hopefully we'll get it out, sometime this year. And like I said, a lot of this stuff is already there if you want to play around with it. I won't recommend using it on operations, though, until we really polish it. And there's a lot more we want to do with it, too. But again, if you want to play around with it, we do develop everything pretty much out in the open, and you're welcome to go take a look at it. So anywho, that's all I got for you. Happy to answer any questions.
Hey, Joe. That was incredible, and clearly I haven't been reading the Sliver release notes close enough. I learned a lot of new things today. I'm just going to check the back scroll, read out some questions if we have any for you.
Sure.
Let's see what we've got. Okay, so question from Skelsec asking how big is the implant, and I believe that refers to Sliver. If you want to clarify that question, just go ahead and type it in the chat.
Yeah, sure. So it depends. So this is one of the, like I was saying at the beginning, right? There's advantages and disadvantages to using any language. Yeah, so depending on which C2 protocols you include in the implant, because we actually remove code at compile time from the implant. If you don't include it, it actually gets removed from the source code. So it can be anywhere from, I think on the low end, we're around 8 megabytes, and then upper end might be 20 megabytes for the implant. Now, what we'll typically do on real operations is we never execute Sliver directly. We use stagers and fairly sophisticated stagers to compress it and load it at runtime. So we typically aren't in situations where we ever have to worry about the implant's file size. Modern networks can easily handle a few megabytes. It's usually like 6 megabytes after you compress it. Maybe even less, again, depending on which C2 protocols you select. And the stagers that we use aren't open source. The core framework is, but some of the extensions we use aren't. But those are written in Rust and C and C++. And so they have relatively small. I think our smallest one is like 30K. And so that's typically how we do it. The full Python, the Python WASI interpreter is about 100, I think it's 120 megabytes or something like that. Although that includes the standard library, which I don't think I need. So I got to look into this a bit more, but I think there's quite a few optimizations to be made on sort of the Wasm module size. I think is mostly because I'm including an extra virtual file system in the Wasm module. And I think it can actually remove that. But Sliver also transparently compresses all of the network traffic. So on the wire, I think it ends up being about 30 megabytes, which again, on modern networks is usually not a problem, unless you're going over DNS or something, which I wouldn't recommend, or I wouldn't recommend using WASM modules over DNS. But typically on modern networks, it's not too much of a problem. And the trade-off is, Go runs on everything because it's statically compiled. You never, again, depending on what you do, you generally don't have to worry about DLL versions or glibc versions or any of that stuff. So I think there's significant advantages to using Go from that perspective. And there's ways of sort of mitigating the downsides to the large file size. So that's been our approach, at least. So.
I had a question, actually, as you were talking about intercepting calls to memfs file system and routing them to the actual file system. How is that performed? Do you mind going into detail on that?
Sure. Yeah, it's actually pretty simple because so with zero basically allows you to specify a call, like you specify a file system object. So Go language contains a file system interface. And basically all you have to do is implement that interface and then pass that to the Wasm module. And I can actually show you the code. Let me pull it up quick because it is relatively straightforward. Let me share my screen again. Okay, so this is GitHub. So you can see here, this is the Wasm extension implementation. And you can see here, when we instantiate the runtime, we can basically pass extra things to it. So this is kind of where we're doing it. So here we're wiring up pipes to standard in, standard out, standard error. But we also pass in this with FS. And this calls make Wasm memfs, which will be implemented in this file here. So this is the make memfs. So basically, it's just going to return a file system interface object because that's what WAS0 takes. So we do a little bit of stuff here to figure out what the volume root is and stuff for Windows, because Windows is always the odd man out when you're writing code. And then it returns this Wasm memoryfs struct, which implements the file system interface, and then we pass in the memfs object, which is in the message. The C2 message includes the virtual file system. So this is the any files that were included in the virtual file system. And then we also have the local file system object here, which we just use the standard library to create. And then here we do maintain a full tree structure for the virtual file system. So there's pointers to pointers and everything. But basically, when there's an open call, you can see here, this is our open implementation. It just checks to see if this is a memfs path. And if it is, it passes it to our sort of like custom VFS stuff. And if not, it just passes it through again to the standard library file system interface. So it's actually relatively straightforward to implement this sort of stuff. Because you just have to implement the interface, right? It does. Sure. Like Wasm doesn't know that it's not talking to a real file system.
Sure, that makes perfect sense, actually. Follow-up question for you. I mean, you kind of touched on it, and I guess honestly, it's the whole premise of the modular network like modification. But do you want to speak more to modular malware in general, leveraging Wasm, and how that might affect Sliver down the road? I know, like, obvious wins are maybe reducing binary size or modifying your stage 0 to include, Wasm loader or something. What are your thoughts around that?
Yeah, I mean, in theory, you could just have the Wasm runtime be your implant, basically. All you need is enough code to talk to the server and retrieve modules. And in theory, you could just implement everything in Wasm. I think the Rust implementation of Wasm is probably mature enough to do that today for the most part. There are some limitations to what you can do, because at some point you might have to call the operating system, right? So I don't know how useful Wasm is for things like allocating memory and doing tricks like that. Because again, you have to, at some point, you're going to have to make executable memory in the operating, at least to like, say we wanted to execute shellcode, right? I don't know how useful Wasm is going to be for that, because the shellcode needs to run outside the Wasm module, right? So I don't know how useful it is for things like that, but certainly you could implement an entire implant, which is basically just a Wasm runtime, and then you lazily load all of the functionality that you want. And then you basically only expose the bare minimum sort of interfaces back to the operating system. In theory, and other people have actually done this, is you can also just pass through the operating system syscall interface, and then force all the code in Wasm to or basically you're removing the entire sandbox at that point, but we're writing malware, so we don't really care about the sandbox. But that could also be interesting, because you could, if you had like a direct syscall piece of code, you could intercept those syscalls and then force them through like a direct syscall rather than going through other means. So there could be some interesting ways to do that. But I think generally speaking, I see it as sort of a platform and operating system independent way to load extended functionality and other types of post-exploitation tooling. I don't certainly you could reduce a lot of binary size as well. And actually, just the other day, normal Go released WASI. So Go 1.21. Then the next release of Go will include just a WASI. Like you can just compile Go code to WASI. I mean, you can do Wasm today, but not WASI. So they've added WASI support to mainline Go. So there's also this other problem where you can only have one Go runtime per process. So historically, this has been a bit of a pain for Sliver, because we can't write DLLs in Go and then load them using Sliver, because the two runtimes don't like each other and everything explodes. So this potentially solves that as well. And I think that's really where we can start pulling stuff out of the default builds of the implant and reduce the file size. But yeah, it'll be interesting to see where it goes. It kind of depends on how some of the standardized stuff works out as well. But yeah, you certainly could basically have a whole implant be just the Wasm runtime. And I think the Wasm implementation in Rust is like less than a megabyte. Actually, the Go was zero is like about a megabyte. So it takes about a megabyte to load the Go version, which is really not that much. At least in Go world, a megabyte isn't a lot. So,
question from the chat: can you get network traffic by opening dev.tcp like a file via WASI?
Yes, certainly today. Yeah. And again, you can specify arbitrary interfaces as well. So you could write your own socket implementation, and that might be what we do for the HTTP like C2 stuff. You can certainly do that today. What you need WASI for is to compile existing code to work with Wasm, right? If you want to take existing code and run it on Wasm, that's where you need WASI. Other than that, you could certainly do. I actually thought, in addition to memfs, I think I'm going to add like a pseudo procfs to so that the Wasm runtime can also retrieve, system information. Like what's the host operating system, that sort of stuff. So I'll probably add that in there as well. And then even on Windows, you'll be able to access sort of like a pseudo procfs through the extension interface. But yeah, certainly today, even you could do dev TCP like communication because you have file system interaction, or you can just do it in memory by defining your own interface. It's just existing code won't work. And ideally, what we would want to do is take the Bloodhound ingester or one of Scalesec's amazing tools and run those on target in memory in the Python interpreter. So that's not quite possible today because the socket interface isn't defined. There's a handful of other things that aren't defined either that are, I think, slightly less relevant. So threads aren't a thing in WASI yet. They're working on a thread specification as well, but there's no concept of multi-threading. Or, none of that works right now. And there's also no garbage collection right now. So those two things, they're not quite as relevant. But there are other limitations, but sockets are, at least for offensive tooling, I think sockets are the really big one. So I'm really excited for that to get sorted out because it just opens up a world of possibilities. So
awesome. We're a little bit over time. I think we'll take one or two more questions if you don't mind, Malak.
Yeah, sure. Yeah.
I'll just give everyone in the chat a second to enter in their questions if you have one. If not, I have one more for you. Any takers? Okay, I don't see anyone typing. So if you don't mind, could you maybe speak to some of the challenges defenders might experience with, malware augmented with Wasm? I know you mentioned that right now nothing is really detecting this, and that's my expectation.
It's too new.
Yeah, given limitations.
Reverse engineering Wasm code is a bit painful right now too. I think Radar supports Wasm, but basically none of the reverse engineering, there's not a lot of reverse engineering tools for Wasm right now. That'll probably change in the future. But at least today, the maturity of the reverse engineering tools available to analyze Wasm binaries, they're not very sophisticated, or at least I haven't seen much that's sophisticated. I think Ghidra might have a plugin or something for it as well, but certainly it's much more difficult to analyze just because, from one standpoint, just because the tools aren't there. I'm sure that will eventually change if it becomes certainly it will if it becomes popular. But again, you can use LLVM obfuscator today to compile Wasm code, right? Which it's already pretty painful to reverse engineer. So you can certainly apply traditional code obfuscation techniques and compiler level obfuscation techniques to Wasm. And that's before you get into messing with and obfuscating the runtime. So I think it significantly increases the difficulty of detection for some of this stuff. Just because, again, we're not calling load library. We're not really calling the operating system for any of this stuff. It's all happening in process. It's all happening in the interpreter. And a lot of the telemetry, even today, at least in my experience, is user space function hooking and kernel space event hooks. And none of that really comes into play with this. Again, other than it's establishing a TCP connection or something like that. But it's pretty difficult to build accurate telemetry based off that small amount of data. I think generally this is also why Sliver tends to perform fairly well against EDR because the Go standard library does, Go has its own compiler. in its own standard library. So when you use HTTP in Go, you're not using WinHTTP or WinINet or any of the system libraries. And this is, again, part of the reason why the file is so big, is that it has to include an entire TCP and HTTP stack when you compile HTTP support. But since none of those DLLs get loaded, none of that stuff gets called, unless you wanted to. We do support HTTP C2 over WinINet if you want, because that's how we get NTLM authentication. But and I really didn't want to implement NTLM authentication. But generally speaking, Go processes load fewer system libraries because everything's statically compiled. And that tends to generate less telemetry on the endpoint just because it's all happening in process. It's more difficult to hook because you have to go into the process and figure it out. We apply obfuscation on top of all of that, making it even more difficult. So I think generally sort of reducing the amount of interaction outside of the process typically reduces telemetry and makes it more difficult to detect, again, generally speaking. And Wasm just allows us to do even more stuff inside the process without interacting with the operating system or anything like that, except for the very bare minimum stuff that we want to interact with the operating system for. So I think that does increase. That's another sort of aspect that makes it more difficult to detect and introspect this stuff, even after the tools potentially catch up, the reverse engineering tools and stuff. I'm sure they will, but even then, you can't go around flagging every Wasm. I mean, maybe you could. Maybe you could just be like, oh, there's Wasm bytecode. It's malicious. But I don't think you could, because this is all in browsers and stuff too, and it's in Docker. So I think it'll be fairly difficult to create generic sort of signatures for. But I guess we'll see.
Yeah, I foresee a lot of EDRs and such choking on Sliver and all of this.
Yeah.
Okay, so we're over time. I think we can end it. Folks, if you have questions, feel free to drop them in the chat. If Joe's kind enough, he might take some time to answer those.
I'll try to stick around and answer them.
Yeah. Joe, thank you so much for joining us. This has been just an awesome talk. I'm really, really happy you took the time to come here and talk about your research in Wasm and give us some insight into what's coming up in future versions of Sliver.
Thanks for having me.
Awesome.